The Sixth International Conference on Computer Science and Engineering and Education Applications. Oscillations at Nonlinear Parametric Excitation, Limited Power Supply and Delay. Mr. Alishir, a.alifov and Mr. M.G. Farzaliev. Mechanical Engineering Research Institute of Russian Academy of Sciences, Moscow, Russia, and Azerbaijan State University of Economics, Baku, Azerbaijan. Model and equations of the system. Figure 1 shows the model of the system. It represents a rod with a spring which is connected to a crank driven by a limited power motor. Figure 1 System Model. The system is nonlinear and taking into account the nonlinearity of parametric excitation and the delay in the elastic force is described by the equations. Here and are the coefficients of stiffness and resistance is the nonlinear part of elasticity is time delay is the moment of inertia of the motor rotor rotating the crank with radius is the speed of rotation of the motor rotor is the driving torque of the motor taking into account the forces of resistance to rotation. Let us represent the nonlinear function as a polynomial using method of direct linearization. We replace it with a linear function. Where and are the linearization coefficients defined by the expressions. Here is the linearization accuracy parameter which affects the accuracy of the method and is introduced into the functional for determining the linearization coefficients. Taking into account 2 equations 1 take the form. Equation solutions. Solutions of equations 3 can be constructed by 2 methods, of which the method of replacing variables with averaging allows us to study stationary and non-stationary processes on the above using. We obtain equations of unsteady motions. The equations of stationary motions follow from the conditions where the expression defines the load on the energy source and the intersection point of the curves gives a stationary velocity value. Stability of stationary motions. It is necessary to check the stability of stationary modes of movement by composing the equations in variations for 4 and using the Rose-Hurwitz criteria. Further in the figures, the steepness of the characteristic of the energy source, which is within the shaded sector, corresponds to stable oscillations. Calculations. To obtain information about the influence of delay on the dynamics of the system, calculations were carried out. The non-linearity was chosen as the linearization coefficient is calculated with the linearization accuracy parameter and has the value for the results of the direct linearization method completely coincide with the results based on the asymptotic method of Bogolyubov-Mitropolsky. Figure 2 shows the amplitude-frequency dependencies where the double-dashed curves correspond to dash-dotted curves to and solid curves to the absence of delay. Stationary solutions do not take place at and the steepness of the characteristic of the energy source, which is within the shaded sector, corresponds to stable oscillations. These sectors should be indicated on the load curve, but for brevity they are shown on the amplitude frequency curves. Criterion of stability 5 in the black field parts of the sectors are performed in the form where there is a rather weak stability. At the curves are unstable for both linear and nonlinear elasticity. There is also the following interesting feature. For in the case of small amplitude, values are stable, and in the case of large ones. Moreover, in both cases, stability takes place in small sections of the amplitude curve. Figure 2, amplitude frequency curve. Thank you for your attention.